Welcome back, everyone. We're back into the 3D shapes of Chapter 2, and we're going to be taking a look today at volumes, and not just any volumes, volumes of a specific type of shape, and these are what we call prisms. Prism is the name of any one of a class of shape where the base at the top, or base at the bottom, and the roof at the top are the same size and shape. And everywhere throughout the duration of its height as you scale down or move up from the bottom to the top is exactly that same shape. Well, that just sounds a bit abstract. Let's take a look and see what we're talking about here. All right, so micro concepts, here's where we still are. We're going to be looking at volume. That's the second to last bullet point on that list there. Okay, so a prism basically is any shape whose base is repeated again and again throughout the climb of the height of the shape. If that's the case, you can take the area of its base, as denoted here, the area of the base, and multiply it by its height. In the case of cuboid, of course, the area of the base is the area of a rectangle, and that's why it says length times width here. So that's a special case. But they're not all like that. It's true for any shape, whether it's one of these kind of triangular prisms here, or this one's a pentagonal one, some obscure quadrilateral one, hexagonal, cylinder, or a cube. All you do is you take the area of the base shape or any of the cross-sectional cuts and you multiply it by the full length of its height, the full amount of its height. So here we go, and that's the simplified version for the area of a prism. You take the area of its cross-section or the area of its base or the area of its top, and you multiply it by its perpendicular height. Now the same is true with cylinder, and a cylinder is a form of prism because if you were to orientate it properly, meaning sitting it on its circular base, then its height would reveal at any point the cross-sectional cut that you would reveal if you were to cut it open are identical circles. So that's what qualifies it to be a prism. Hence, its volume is the area of its base, which is pi r squared. You can see that revealed in the first couple of factors here, pi r squared. But then that in turn gets multiplied by h, which is the perpendicular height of the object. And these formulas are all given in your formula kit. Right, so let's take a look at this. Now, this says there's some lake somewhere. It's got roughly a kidney shape to it, but that's not an official geometric term. So just to give you a guide, it's kind of irregular. It's got kind of bulbous at one end there. Its area at the top of the surface of the water is 85,000 square meters, but the depth is 28, and it's an average depth, so we assume it's like roughly uniform throughout, even though that's unlikely. Estimate the volume of the water in the lake in cubic meters. Well, to do that, we have to make a couple of observations about this. We assume, number one, that the water in the lake has a 3D shape, and this hopefully will be prism-like, meaning that all the way down through the entire 28-meter depth of the water, that shape maintains its size and its actual shape. So we're going to take the area of the cross section and multiply it by the height of the water. Now, obviously, this isn't a height of water; it's a depth of water. But it's the same thing as whether this lake was, an aquarium sitting on dry land, or if it's down under the surface of the ground. So the height of the water is the same as the depth of the water, and we take the area of the cross section at the top and we multiply it by its depth, and that's 28. And your calculator would tell you that's 2,380,000 cubic meters of water. Other shapes we're going to be dealing with, cylinders here, for example. If you want to find its volume, you take the area of its cross-section top, as denoted here, which is pi r squared. That's the area of a circle. And we take that there, and we multiply it by its perpendicular height, which is that the height is perpendicular to the radius, so we multiply 7.5 by the area of that circle, and we get 94.2 cubic centimeters. That'll be the last one of the day. Tougher one. It says the volume of a triangular prism. Okay, looks like a really squished up Toblerone chocolate bar here. Its base is an isosceles triangle. Remember, isosceles triangle means that two of the side lengths are identical to each other. And the angle between them is 130 degrees. Gosh, I wish they had shown us what that looks like. Now, the height is 15, so we've got that covered. I need to focus on this isosceles triangle so I can learn more about it. And this looks exactly like what we just recently did in trigonometry, where the area of a triangle non-right angled triangle is the product of its two lengths that are containing an angle times the sine of that angle and then divided by 2. So that's going to reuse a recent formula and extend it into new territory. So we say there inside the triangle I wrote down, it's 12 times 12 times the sine of 130 and then divided by 2. So that fulfills the volume formula, the area formula for a non-right angled triangle. And if I want the volume, you simply take that area and you times it by its perpendicular height, in which case is 15, and all those numbers jammed into your calculator is 827 cubic centimeters. I hope that makes sense. I'm right here to help you if there's anything that needs clarification. Where are we? We're in 2G, and so some of you still have outstanding exercises for 2F. That's understandable. Having done it so recently, we had other things going on. So 2G is right there. Go ahead and you can work on those. There's a bunch of questions there. Nice volume questions, not too tough, but important, and they're on the syllabus, and they will be featured on your exam. I've selected 1, 2, 3, and 4 because I think they feature fewer redundancies and give you a good challenge. Again, I'm here with you. I want to help you. So let's try and get this done right away. Okay, good luck.